Good afternoon. Welcome to the second of our events in this term's series on new frontiers, pushing the boundaries of science and technology. Tonight we have Dr. Colin Wilson come to talk on expanding frontiers in space exploration. So Colin is in the Department of Atmospheric, Oceanic and Planetary Physics. He's also an interdisciplinary scientist for the European Space Agency's ExoMars 2016 mission. His main interests are Venus and Mars, and he was Science Operations Coordinator for ESA's Venus Express satellite. He's developed instrumentation for Mars landers for atmospheric science, and he's developed mission concepts for future planetary exploration, in particular Venus mission proposals. So we look forward to being taken to other worlds. So over to Colin.
Thanks for the introduction. I'm not actually sure what you're supposed to take home as a message from this. Is this what us hardworking government-funded scientists do when you're not looking? Not sure. I'm also not sure how the astronaut's going to actually sip his beer. It could be fatal. But anyway, so I shall take you on a bit of a whirlwind tour. It's late, so there'll be lots of nice pictures and things. But let me know if you have any questions about it. So first of all, why are we exploring? Why are we pushing the boundaries? If you ask different people are motivated by different reasons. So being scientific researchers, we look first at the scientific understanding we can gain from looking at other worlds, and I'll summarize those in a minute. Some people just think that exploring is cool. They're very just attracted by it. You know, sometimes when we say we work on planetary exploration, people go, wow, that's great. And other people just go completely blank, sort of, and why would you do that? And it's sort of, it's not directly relevant. So for them, you start launching then into these other ones. So this was maybe more relevant, particularly in the Cold War era, when, for example, you had the docking of US and Russian Soviet spacecraft. It was really important as a sign, a signal. When we're talking to government, we list a lot of these things, return on investment technology spin-offs. So we always have helpful enterprise folks coming around, seeing what clever technologies we've come up with to spin out and make money from and contribute to society and industry and economy and so on. And of course, space exploration, the sort of planetary exploration and even space science, it's like the Formula One is to the car industry. It gets all the attention in the press, but the far more prosaic applications, which is where the vast majority of the space industry is based, is for applications like space navigation, GPS systems, Earth observation, weather satellites, and of course telecommunications like Sky television and things. And so they love the fact that some fraction of space expenditure is on these glorious high-profile missions because it brings more people into the field and gives them a good rep. Related to that is, of course, that we can give talks and encourage school children and even grown-ups to be curious and inquiring of their world. Finally, some people think this is the ultimate reason we should be preparing for imminent departure to settle on other worlds, which I won't go into much more today. But so in terms of science, I'm not sure if we can dim the lights a little bit, maybe you might see a bit more of this, but especially 20 years ago, 20, 30 years ago, it might have been just planetary exploration might have been a question of just seeing what the different planets are like and totting it up, putting it in a table and keeping it on a shelf. What some pejoratively referred to as stamp collecting. But now this has been given a particular urgency since we've discovered lots of planets around other stars. So I think the confirmed number of exoplanets is upwards of 3,000 now. And they're being detected at exponentially growing rates. And given that I think it's 100 billion stars in our galaxies and 100 billion galaxies, or numbers of that order, And the mean number of planets per star is 1, at least. There are billions upon billions of planets out there. And so understanding the diversity of planets, starting with those in our own solar system, and understanding the different pathways through which they can evolve and form, and the different conditions you can find on them, becomes quite interesting. So this particular set of 3 planets is supposed to be an early Venus, Earth, and Mars. Since my own research has been focused quite heavily on Venus, I will lean heavily on Venus examples throughout this talk. In this particular case, if you were to visit Venus now on the surface, you'd find it's extraordinarily hot at 450 degrees centigrade. Mars tends to be quite cold. It can get up to 0 degrees on a warm summer's day at midday, but the average temperature is more like -60 or so. So, whereas Earth, of course, in the middle is just right. And so understanding the diversity of how these different climates evolved, particularly given the geological evidence that both these planets might once have had water, liquid water on their surface, is something we're keen to figure out. So just to hammer that home, again, lazily I've borrowed this slide from a Venus presentation I had. Why have these planets ended up different? This is again Venus, Earth, and Mars. So Venus should be the most Earth-like planet we know of in our solar system, being almost exactly the same size and being formed at around the same time out of the same materials. You may think, it's simple. Venus is hot because it's closer to the sun. But it's not that simple because it's completely surrounded, completely enveloped in very reflective clouds. So it reflects away so much sunlight that the amount of heat it absorbs from the sun, the amount of energy it absorbs from the sun today, is actually a little bit less than what you have on Earth. And so instead, the reason it's so hot is because of the vast amounts of atmosphere it has. It's had a runaway greenhouse effect. It hasn't managed to capture all the carbon dioxide in its system down in carbonate rocks as we have on Earth. If we were to cook all the limestones and carbonate rocks on Earth, we would release an amount of carbon dioxide into the atmosphere very much like Venus. So again, supporting the hypothesis they were once much more similar. So the question we're trying to answer here is, was there ever liquid water on Venus? And if so, could life have evolved there? Or could even, some of the precursors to life, would you have had amino acids forming? Would you have had some of the precursors to biotic molecules? And we can also consider runaway greenhouse scenarios, which might happen on Earth. So related to the question of planetary evolution, how did the environment and habitability of the planet evolve? One of the tasks in front of us is to look through the solar system to find where can we find water in the solar system, and in the universe, in fact. Where can we find more complex molecules? So these are all molecules which have been discovered outside the Earth. So amino acids, for example, you find in comets. Some of these other things, carbon monoxide, we can observe in other atmospheres, and some of these other compounds have been found in meteorites which have fallen to the Earth, at the interior of meteorites, where various lines of evidence show that they came in with the meteorites rather than Earth contamination. Titan is particularly interesting because it's the only nitrogen-based atmosphere other than our own, which we know of, and it's full of hydrocarbons. So methanes, ethanes, really long, complex hydrocarbons. So there's some very interesting chemistry going on there. So beyond then this formation and evolution and where are we all from, there's the rather more boring to some, but rather exciting to us in the physics and earth sciences department, of just having a parallel laboratory in which we can look at different aspects of the geophysical system. So atmospheric science, radiative balance, atmospheric dynamics, these are some examples. Even something like sand dunes. We study them on Earth, and we know there's a certain relationship between the sizes and slopes. So what happens when you change the strength of gravity and go to a different planet, or change the atmospheric density? How do the dunes differ? And we've now got dunes to look at on Mars and Venus and Titan as well. And we can check that our physical understanding of the laws of geophysics and so on is correct. So this keeps us busy in our day jobs. I thought I would just go through generically, if you find a planet and want to go out and explore it, or any target in our solar system, our exploration tends to follow these steps. So first you have to detect it, or presumably you first have to hypothesize that it might be there and get your telescopes and get your detecting tools ready. And then once you observe it, then the next step is to, and you can do quite a lot from Earth, then the next step is to send a spacecraft there. Typically, the first step is to go so fast, or in fact, I've got some examples. So the first man-made object in space, Sputnik, which was 56 or 57, 1957, and that was followed very soon after by the first attempts at planetary flybys. I particularly like the early Soviet planetary landers. These look perhaps a bit like something you'd construct in your garage, but of course there weren't space equipment labs then, so we may laugh, but they constructed a vast number of spacecraft in a very short space of time. So that was very shortly followed by the first successful planetary flyby, which was of Venus in 1962, and then first flyby of Mars in 1964. So remember, you've used all this rocket fuel to get you to a planet, and unless you use an equal amount of rocket fuel to slow you down, you're just going to fly straight past it. And so Mariner 4 did fly straight past Mars, and it managed to return some images from the surface, including this one, showing that there were craters. In fact, it looked very much like the moon, a lifeless cratered body, unlike the sort of lush paradise some had been perhaps hoping for. But so that shows you can get quite a lot of science out of a flyby, even with these primitive instruments. And so the flyby spacecraft is still a useful tool in our arsenal now. So rather famously, the New Horizons spacecraft flew past Pluto in 2015 and got a huge set of really beautiful images of the surface of Pluto, which until its flyby had just been a little smudge in sort of telescope images. So once you've got basic images of what a planet looks like and maybe a first order map of its surface, the next step is to have a more sustained presence and slow down at the planet and go into orbit around it. And so, again, some early example of orbiters in the lunar program, once they decided to go to the moon before sending humans, in order to get a good cartography of the moon, they sent some orbiters. And so both the Soviet orbiter and a NASA orbiter both first arrived at the moon in 1966 and started obtaining images in addition to their maps, like this, the first sort of Earthrise above the limb of the moon. And orbiters are really the bread and butter of our planetary science ever since. A particularly successful example here is the Cassini orbiter. So this was a NASA-ESA joint mission launched in '97, and it's still orbiting to this date, although it is coming to the end of its mission, and rather than let it have the possibility of crashing into such an interesting object as Titan at the end of its life, in an uncontrolled way once it's run out of fuel, they're instead going to crash it into Saturn, so that so there's no chance of contaminating Titan, of which more later. Interestingly, we, here in Oxford, built parts of the infrared spectrometer on this mission. So the reason I'm here standing in front of you is because we do build some of the science instruments for these exploration craft. This was before my time, I should say. So having orbited and having a good look at the planet, then the next phase is to land on the surface and maybe take samples and measure things directly in situ. So arguably the first entry into a planetary atmosphere came through the Earth exploration program. This is Yuri Gagarin's capsule, so first successful manned re-entry. It's alarmingly charred if you look at it in detail. This is an unmanned craft which landed on the moon. It just so happened they landed their Apollo capsule next to it so they could take nice pictures of it. Otherwise, we don't have the benefit of such handy photos of our landers deployed on other planetary surfaces. But so this is still, having simple landers, simple probes and landers is still part of our arsenal today. So the Cassini spacecraft carried Huygens to Titan, the moon of Saturn, which is 1 billion kilometers away, and successfully landed this probe there. So that's the most distant object landed on another world, which we've sent to date. But having landed in one place, the Huygens probe, for example, did all its science on the way down and then came to rest. Next thing you want to do is have some mobility on the surface. So if there's a really interesting rock over there, you want to get to it. And so the most glorious of these now is the Mars Science Lab, also called the Curiosity rover, which is currently roving around Mars. And this has a magnificent set of tools. This, by the way, is the nuclear power station, which it carries around on its back to give it enough power. Because solar panels are unwieldy, and you need a lot of them to get the amount of power it needs to do its job. It has the very 21st century capability of being able to take selfies, of which this is one. And so it's been rarely snapping selfies and sending them back. You can see them on its Twitter feed. It's got a magnificent set of instruments. One of the most dramatic is it's got what's called ChemCam, where once you see an interesting object in the camera's field of view, you can fire a laser, a high-powered laser at that rock, even if it's 10 or maybe up to 20 meters away, and vaporize a little bit of that rock using a laser. And then a spectrometer, which is looking in the same direction, can analyze the spectrum of the chemicals released from that. So it is rolling around Mars, firing lasers at rocks and measuring the composition, which is pretty cool. The next version of this is going to include a microphone as well, so that it can hear as the rock gets burned to a crisp, because that gives it some measure of the energy deposition in the rock. I kid you not. So although they're very spectacular, these rovers, and they get magnificent images, it's important just to remember that these are not Ferraris, these are not, sports cars. They don't go whistling across the surface at great speeds. This is the entire distance covered by, this is now out of date actually, but for example, the Opportunity rover went a total of 26 miles in its life. I think they released this in 2015 when it had gone the length of a marathon. And so that's a little bit further than the lunar rovers went, which could go much faster since they had someone in command at the steering wheel driving it and making those decisions in real time. Because otherwise you can't drive these rovers with a joystick, because the two-way light time, by the time you see a rock in the image at your dashboard, it's too late to avoid it, because the light's taken several minutes to go back and forth from Mars to Earth. But these are not the mobile exploration craft which have gone the furthest on other planets by a long shot, because in 1984-85, the Soviets deployed 2 balloons in the atmosphere of Venus, which were carried by the winds on Venus and traveled over 11,000 kilometers. So although it's slightly unfair to put them in the same categories as the rovers, because these were just blown passively by the wind, we just like to remind our Martian colleagues of this every once in a while. And it remains an incredible achievement, very sort of Jules Verne, very sort of 20,000 leagues under the sea, deploying balloons and going halfway around the planet. So we've been trying to repeat this feat. These were viewed as being the vanguard of a fleet of planetary balloon explorers. But unfortunately, the Soviet economy didn't do so well in the decades after this, and they weren't able to follow this up with a more complex craft they were expecting to. So once you've roved around the surface or around the planet, what's next? Well, this is a problem that the Mars exploration program is facing. I mean, we can send orbital measurements of ever increasing sophistication, and there's a seismometry mission planned for launch next year to finally look at the interior. But after that, one of the next stages will be sample return, to try to get samples from the surface and bring them back to Earth. But that's a very big undertaking, and the funding isn't quite in place. But but then the next thing would be sending humans. And then eventually, according to the vision of colonizing other worlds, then you're trying to make the case towards a sustained presence like that, which we have, for example, in space or at the South Pole now, which have been inhabited continuously. So just for fun, I thought let's try to sort of make a graph and how our progress for a few representative targets has evolved through time. So if you think in 1956, there was already certainly visits to Antarctica. In fact, I think the first base at the South Pole was established around this time, so that should arguably be the first permanent base. This line should perhaps be longer. And at that time, we'd only observed all these targets and hadn't gone very far. Things moved fast. By 1966, we'd had flybys of all the nearby destinations. And of course, we'd had the first visit. Yes, the first visit to the moon was almost there. We certainly had the first landing on the moon by then. And then as we move forward in time to 1990, we then had, I'm slightly cheating here, I've counted the balloon as a mobile platform here. I just wanted to highlight the time when Venus was doing well relative to Mars. Mars then got its first rover in 97, so there's a bit of a gap before something happened. I think the formatting of this has also been slightly, no, okay, we've had human visits here. But the question is what'll happen next? So this is a 25-year gap. When you have the next 25-year gap, we've filled in a few of these bars on this bar chart. But of course, the difficulty is that to do much more, it gets increasingly difficult. You know, some of these objects are very far away, which is why we've only got this far with Pluto now. And for example, human visits out to comets is going to be a long time coming. I thought I'd switch gear a little bit and talk about some of the tools we use to gain knowledge when we go to these other planets with imagery and orbiting. One thing is simply sending a camera on a flyby craft or an orbiter gives you vast amounts of information. So just to illustrate this, the big Viking mission, the big Mars mission NASA sent in the 70s was called Viking. There's Viking orbiters and Viking landers. And it sent back pictures of the whole surface at about 100 odd meters per pixel. And that showed these craters, and that gave us maps, and geologists went away and studied them, and it looked like a fairly lifeless surface. It was only when NASA came back 20 years later with much higher resolution imagery, so increasing the spatial resolution by an order of magnitude, you can start to see interesting features like what looks like water-deposited features here and perhaps runoff here. And a decade later, with much higher spatial resolution, you can really zoom in. Here we've got color as well. And you can start studying these features in detail. You can start seeing things move, new gullies forming, colors changing the edge of the gullies, revealing that this isn't the sort of completely lifeless, dead planet, which it had been thought of as before, but actually an active changing planet now. And so there's lots of things to study. And of course, for completeness, we now have imagery of much higher spatial resolution from the ground, of course, down to centimeters and millimeters. So revealing features like these veins in the rock, which are characteristic of having liquids seeping up through cracks in the rock and leaving their mineral deposits, which is again consistent with a wetter aqueous past. This, by the way, is a meteorite which has fallen from space on Mars, just to know that they can get hit by meteorites too. So spatial resolution is one really useful thing. The other tool at our disposal is something the astronomers have been using for ages as well. It's just exploiting different wavelengths and different frequencies because they tell us completely different information. So I've got handy slides about, you guessed it, Venus here to illustrate this. If you looked at Venus in the visible, this is what you see. It's a bit like a billiard ball. This is an image taken by a Mercury spacecraft fairly recently, so this is a true color image, I believe, red, green, blue filters. And that's what you see. So what you're seeing is light reflected from the cloud tops. And this is, in fact, why Venus is so bright in the night sky, because it's completely covered in reflective clouds. But it's not very revealing. So if you move out to shorter wavelengths in the ultraviolet, then you reveal lots of cloud features. And this becomes much more interesting for us atmospheric scientists, especially because you can, first of all, you can look at the spectrum of this to see what the composition is and see what it's made of. You can also look at how these features are being blown across the planet, so you get wind fields and meteorology. But that's still at the cloud tops. Here's an image obtained in the thermal infrared. So this is wavelengths at which all objects radiate according to their temperature. So this gives us a measure of cloud top temperature. And the Pioneer Venus mission back in 1979 got some very intriguing snapshots of the polar regions showing a very enigmatic feature on what was otherwise a fairly featureless temperature field. And is by coming back with the Venus Express spacecraft a couple decades later, 3 decades later, in fact, that the European Space Agency managed to get far more detailed pictures of this. In fact, moving images as well. So that enables us to study cloud top temperatures and other features. There were also other frequency bands where photons thermally emitted, so thermal emission from the deep atmosphere and surface, escape through the clouds to space. So this is like backlighting for the deep lower cloud layer. So this lets us get a real three-dimensional perspective of this thick cloud deck, which is about 20 kilometers thick. And so we're studying that at the minute. But you can go to even slightly shorter wavelengths than this and study emission which is coming up from the surface, which lets us map surface temperatures. So first of all, that gives us a measure of the mineralogy of the surface, how black are the rocks, how red are the rocks, which gives us some constraint on their composition. And so, for example, some of the blackest regions are right next to what we know to be volcanoes, and so it suggests recent lava flows. But also by imaging the same region several times, we've seen apparent changes in temperatures on the flanks of a volcano. So there's a volcano here, and on the flank of that volcano there was a sudden change in temperature, and then it cooled off later. So we think this might be a volcano erupting between these dates. It's rather amazing to know exactly when that volcano would have erupted. So we're interested in sending a follow-up mission to find this. But all this light from the deep atmosphere is bouncing off all the cloud particles on the way up through the clouds. So it's very diffuse, and you can't get high-resolution imagery because it's like looking through a film of like a diffusing film. So we can use radar. And so in 1989 there was a big US-led radar mission called Magellan, and that gave us global maps of the surface, revealing, yes, it was covered in volcanoes and lava flows and tectonic features and so on. So, and looking to the future, we can again use radar. Some techniques allow you to look very sensitively for changes on the scales of centimeters or even millimeters for changes, because we'd really like to know whether these volcanoes are active or not. And so here is a simulation. Let's see if this has made its way. These are measurements of the surface deformation of Etna in Sicily. So you're seeing vertical displacement on sort of centimeters to tens of centimeter scales. And what you're seeing is slow inflation followed by rapid deflation when there's been an eruption. So that's a small eruption, and then I think here comes a bigger one. There you go. These are eruptive events happening. So this is the kind of data set, in principle, we could get through the clouds of Venus from orbit. So that's something we're planning. So just because we have some data sets doesn't mean we don't want more. That's the nature of scientists, of course. So that was just a little illustration of how really trying to exploit the full range of the spectrum helps us understand different levels of the atmospheric system and different aspects of the planet. Something else, we've talked about spatial resolution. The other thing is, as well as just imaging in different parts of the spectrum, really getting those spectra with high resolution. So we know on Mars, for example, that the main atmospheric constituent is carbon dioxide. That was measured even from Earth in fairly low resolution spectrometers. This then shows a very high resolution spectrum. As you vary the wavelength, you get different absorption from molecules, and they have a characteristic absorption for different molecules. But you need extremely high spectral resolution to identify different molecules. And the interesting thing about this spectrometer, which has just arrived in orbit around Mars a few months ago, is it'll be able to measure methane down to abundances of only a few parts per billion. There have been very enigmatic measurements of methane. The reason everyone's excited about methane on Mars is that the main source of atmospheric methane on Earth is the biosphere. So plants, decaying vegetation, cows, ants, you name it. So that's what everyone's really excited about as a potential source of methane. It's worth mentioning there are potential other sources involving water and particular mineral classes which can generate methane. Well, by studying where this methane emission is occurring, because it appears to be spatially variable, temporally variable, we can try to disentangle these mechanisms. It's also worth pointing out that it can be stored for a long time in the subsurface. So it's not necessarily the case that these things these processes are ongoing now. Perhaps there's just been long-term storage. And there's a whole range of other chemistry which we have to understand before we can answer the question. So although we are trying to answer the question, as generations before have, of whether there's life on Mars, the answer is we'll need a bit more time and funding probably as well. So, but watch this space, we're looking into it. I'll mention the importance of spectral resolution also in the context of exoplanets. So you saw these magnificently high resolution spectra we can now get from Mars with a spacecraft at Mars. For exoplanets, this is planets observing other circling other stars. It is unsurprisingly much more difficult. It's slightly fantastical that we can get any information at all from these other planets, but these now are spectra from the other planets. Now, the line through the middle is the predicted spectrum from the other planets. In this case, it's the transit spectrum, which I'll explain in a minute. So this is what various computer models are telling us the atmosphere should look like, and the dots are measurements from ground-based telescopes and from space-based telescopes about what those planetary atmospheres should look like. You may be impressed, you should be impressed by the high fidelity, the high spectral resolution of these computer-generated curves. But remember, we're trying to match these observations. So if you're trying to match this predicted spectrum to these points, you've got a lot of latitude. Here, you've only got a couple of points to match. So the problem is what we would call under-constrained. There are many, many solutions which would fit a mere 2 wavelengths in this spectrum. So the point being that exoplanetary science, it's amazing what we can already get now. So for example, the slope here tells us about the cloudiness of the exoplanets, so we can detect whether exoplanets have clouds. Some of these peaks tell us whether they've got metal in their atmospheres. But this is a field which is evolving rapidly, and as the spectral resolution improves, we'll be able to achieve vastly more. It's worth remembering that all these exoplanets, the discovery of exoplanets in the first place is a testament to the incredible accuracy and incredible precision to which we can build scientific instrumentation now. So the first discovery of exoplanets they came from looking at a star like this and looking at the spectrum of light which comes from the star and noticing a very slight wobble, a slight shift in absorption lines in that spectrum. So this is what you would get if you for example, shone the light from that star through a prism and shone that onto a screen. But the shift of these lines occurs because of the Doppler shift of the planet, of the star itself moving to and from you. And so when the planet's moving away from us, The star is moving slightly closer to us, and you're getting a Doppler shift in that light. But that Doppler shift is a tiny proportion of the wavelength. So it's less than a millionth of the wavelength of that shift. So you need a spectrometer which is measuring the position of these lines to a supremely high accuracy, which they do now, which is how we've managed to discover these. This is one of the ways of detecting exoplanets. Another one is transits. So if you watch this, I think this is supposed to be a video. Video's not working. If you can imagine a planet passing in front of the star, stars tend to be much bigger than planets. So an Earth-sized planet passing in front of this star, as viewed from far away, would be just this very small dot passing in front of the star. And so if you watch the light from that star, you'll notice a very small dip in the light from that star. But because the planet's only obscuring a very small portion of that star, this dip may be a millionth of the brightness of the star. So you need to watch the brightness from a star and measure it to an accuracy of parts per million or less in order to detect that a planet's passing in front of it. So the two main techniques for exoplanet discovery require spectral measurement, spectral precision to less than a tenth of a part per million, or radiometric precision, being able to measure the brightness to within about a part per million or less. So it's only in the last 2 decades or so that 2-3 decades that we've built instruments to this precision to measure these, to be able to detect exoplanets in the first place. Finally, another way of imaging exoplanets, you think, well, let's just take a picture of it. Well, remember that stars tend to be about 1 billion times brighter than the planets around them. And you're trying to look at the light from the planet. So there are various tricks you can use to try to shield the telescope from the light of the star. But the planet is less than 1,000th of a degree away from the star, very, very close to the star. And so to image something so faint next to something so bright has again required true feats of engineering to be able to achieve this. Which is how we've managed to discover all these exoplanets. So this is just showing the huge variety of different masses of exoplanets discovered at different distances from their star. So I also thought, because there was something in the series description about some of the ethical and moral questions which come to light in some of these expanding frontiers activities we're doing. Planetary protection may not be a term you've heard, certainly not in this context, but it's something we have to wrestle with, particularly for Mars exploration. You may have wondered, if you see pictures like of this, of people assembling Mars missions like this, why they're wearing all this protective equipment. It dates back to a treaty 50 years ago, in fact, the UN Outer Space Treaty. So states party to the treaty will conduct exploration so as to avoid harmful contamination of those planets, but also to avoid contaminating the Earth by bringing extraterrestrial matter back. So in short, writing it the way it might be written in a swimming pool, so to do not contaminate other planets, but do not contaminate Earth. So what does this mean for us in practice? Well, we have to, the simplest thing to do is just sterilize everything before you send it up, right? You make your equipment, you stick it in an oven, for example, at 125 degrees centigrade for 100 degrees, which will kill most things we know about and worry about on Earth. The problem is if you just do that, then you're sending lots of dead bugs to Mars as well. And if you then detect a dead bug, if you detect a flu germ or something, you'd write a paper about it and be lauded, but maybe that just comes from the technicians who had a cold on Earth as they assembled it. So therefore, you have to also assemble everything in ultra-clean facilities to minimize the number of potential contaminants. And also, we need to worry about contaminating sites. So for example, this Cassini mission, which has been very successful for a very long time orbiting the Saturn system, there's a risk that when it comes to the end of its propellant in its tanks, that it'll impact Titan. And so to avoid the possibility of that happening and potentially contaminating this interesting site of Titan, they're going to crash it into Saturn instead. We categorize different targets according to how important it is to worry about this. So, for example, you're pretty much allowed to crash anything you want onto the Moon or Venus because they think nothing's going to survive. But as you move to more interesting targets like Mars and so on, then it becomes more important to worry about, particularly if you're going to land there. You now have separate categories. So if you've got a life detection experiment in a gully on Mars, then you need to take extraordinary precautions. Whereas if you're landing a seismometry missions on a dusty plain, then it's not quite so critical. So if you do any of this, then you go on a planetary protection course and you can get a certificate saying you're a planetary protection officer, which is a great card to get out of pubs, but I'm told. So what do we have to do? Well, we have to keep everything clean. We have to sterilize everything as discussed. But the other thing is you do a lot of paperwork demonstrating how clean your clean rooms are and how abiotic your abiotic controls are. One of the tools we've had, you may be wondering about this, is to test for the presence of bacteria of different types. There's various reagents you can use, there's various tests you can use, but one of the most broad tests you can use takes the blood of horseshoe crabs, which contains enzymes which are, because they are so biologically ancient, they're sensitive to a very wide range of biological material, it turns out. It's not my field. So this does not occur in Oxford University, it occurs in labs elsewhere. They remove some of the blood from horseshoe crabs, which are then released back into the wild. This doesn't harm them, apparently. And this is then packaged off and sent to clean rooms such as ours, where we can use it to test the cleanliness and the bioburden in our clean rooms. So why do we worry about what's going to happen with these planetary protection rules? Well, it's all very well if we're sitting here discussing a Mars flyby craft, but what happens when you set up a Mars base? Particularly, this Mars base is called Mars 1. You may have heard of it. Is by the people behind Big Brother. Suggested that we're going to set up a colony on Mars. We're going to pick people in a Big Brother style, and presumably not vote someone off the base every time they do something wrong, but vote them out of the Mars program every time they do something wrong. And it's going to be a one-way trip. So you can imagine just the detritus piling outside this lab. It might look rather like, this is a landfill outside McMurdo Base in the Antarctic. I stole this from a Greenpeace site. So there's some real considerations as to how rigorously you're going to enforce these rules. So in principle, everything is put in sealed containers and then eventually returned to Earth when the colonization has got sufficiently advanced to have return vehicles to bring the rubbish back, but that might be some time. So as commercial partners get into the game, who's going to pay for their waste removal costs and planetary protection costs? That's one of the things which will be in our future. Some of the other things which you might want to consider is the way forward to achieve rapid progress in expanding frontiers and planets, to collaborate between nations. So, for example, the International Space Station, or the current Mars exploration program, which started as a European Space Agency only mission, then became a ESA-NASA joint mission because the costs were ballooning. Then NASA pulled out and it became an ESA-Russia mission. And with all these machinations and redesigns, there were launch slips, and so it's taken a long time to get off the ground. So that's one way of doing it. But of course, the other way to do it is to compete. And of course, this drove America and the Soviet Union to vast achievements in the 60s. And we may be going into a similar era now. So NASA has been very much dominant at Mars, but ESA have a couple of craft there now, and it's going to get crowded there soon. So China is arriving soon. India's got one craft there already, and it's got a lander coming up. Even the United Arab Emirates have a mission coming up. Just met some of their scientists last month. And then even, so Elon Musk with SpaceX, this is the man behind Tesla and PayPal, I guess, is planning to, well, he's announced he wants to send his a rocket capsule there in 2018. It's looking as if it might be 2020, but certainly a new era is upon us. But so a question you can perhaps think about is which of these is going to lead to faster progress and greater achievements? And similarly, on the same note, which of these is likely to lead to greater achievements? So I will leave this in your hands. There's a lot to come in the next few years, so continue to watch this space. Thanks.
Thank you very much, Colin. That was fascinating. We have a few minutes for questions. Please be aware that we're filming this, so only ask questions if you're comfortable with being filmed. Please, take one there. If you just wait for the mic to reach you, then everyone can hear.
Is there scope for really tiny explorers, micro-miniature things?
Oh, I thought you meant tiny human explorers for a while. I was looking for volunteers.
Control that, yes.
So yes, if you've been following the Martin School programs, last term there was a talk, I believe, by someone from the Breakthrough Foundation. So there's talk of what would we need to do to get to that next step for exoplanets, which would be a flyby craft. And the thing is that the distances involved for exoplanets are so vast that the way they can contemplate doing it in any sort of sensible lifetime is to take a 1-gram spacecraft, so little, completely micro-miniaturized thing, and shine an enormously powerful laser at it to give it an enormous acceleration, accelerate it to an appreciable fraction of the speed of light within a few seconds, I think. And then it would still take 80 years, I think, or something to get to the next star system. You then have very real questions about the feasibility of getting any information at all back from that. If you think of what kind of data rates you'd get back from that, it's questionable whether you can even get a single image back. But that's something people are working on, yeah. On the closer scale, many of the planetary missions we're sending now, we're thinking of sending little CubeSat-sized things, so 1 liter to 10 liter sized spacecraft, which are increasingly powerful now. And so that's something we're trying to deploy.
If you just wait for the mic, because the acoustics, the people behind won't hear.
I'm completely a layman in this area, so it's just podcasts and various things that I've listened to and read about. One thing that, and what you covered on the sort of spectrometry area is, and what seems to be incredible is the increasing amount of detail that you can capture just from light that's being received. So, it was something over a year ago, I was listening about this sort of L structure that's being set up somewhere in the US, somewhere I think in some plane, that can capture just the most incredible detail of light. And it seems to me that you can almost substitute a lot of what you would do 10 years ago or 20 years ago of sending out a probe with just capturing that light. And I'd be curious to hear what your colleagues' estimations are in the future of how much you can substitute by simply receiving light and evaluating that rather than sending out these probes and the whole competition that you've just made mentioning.
So they do incredible things from ground-based telescopes, and they continue, the whole field of astronomy and cosmology has been based on those. But there are some wavelengths where the atmosphere is opaque. So infrared wavelengths where a lot of the chemical information about other stars or galaxies or planets are, and you simply cannot observe from the ground at these wavelengths, also in the ultraviolet, which is why you have some of the best observations are from space. So the Hubble Space Telescope does take ultraviolet spectra of other objects, which you can't obtain from ground, and big infrared observatories are also planned. So there are limits to what you can do from ground.
Thank Thank you for the fascinating talk. NASA is predominant in Mars exploration. And do you have any other plan to explore like Saturn independently? I mean,
when you say me,
I mean the European space base.
So there's a steady stream of competitions both at NASA and within ESA, and there are, for example, there's several missions in competition now within ESA, which includes, certainly they include Europa missions. Europa is a moon of Jupiter. And there are plans looking forward to Saturn missions. Yeah, so there are, yes, the short answer is yes, there are.
Thank you for a great talk. I had one very quick question, and that is that on Saturn, hexagonal wind formations have been viewed by various orbiters. I was wondering whether the clouds on Venus show any shaping by winds or whatever.
So it turns out that when you have an atmosphere on a planet, and the planet's rotating, you almost always get some sort of polar vortex feature, simply because you have fluid moving in a circle and you get oscillations in that fluid. And depending on various parameters like how fast the rotation is and gradients in temperature and composition and so on, sometimes a six-sided structure is preferred, and on Venus it seems to be much more unstable, much more unsteady, and tends to be mostly two-sided, as you saw in the very initial images. But that on Venus it seems to be unsteady and sometimes three-sided. But you also have polar vortices on Mars and on Earth, and they each have their distinct different circulation regimes which change the shape.
Thanks.
There's one back here.
The Curiosity rover is the size of a small car and has, I think, over a dozen electronic cameras aboard it. And yet it has not one single microscope, not even the equivalent of a child's toy microscope, nothing more powerful than the hand magnifier. Why is that? It has been suggested that it's because people want to spin out the exploration of Mars. There is going to be a follow-up mission and probably a third mission with a very similar rover. Why is there no microscope aboard Curiosity?
You could go around certainly all the science groups, all the planetary science groups, and probably around the public, and they'd all say, why is there no, and there's something else. So for example, we are atmospheric scientists. I build wind sensors, and there were no wind sensors on the previous rovers, and which had us going around saying, why haven't you put a weather station on this rover? So there's always something which is missing. I'm trying to remember, I think the previous rovers had a microscope.
Well, the Curiosity is where you might want to cover a large tract of terrain and look for microfossils, any hint like that, even if no life, there's still reasons you want to look at rocks at very fine detail. I mean, I think your point is you can't do everything with rovers. You have some cameras and no microscope.
And I think there might be a letters page at NASA you could submit your complaint to. No, I mean they have a handless imager which gets you down to less than a millimeter. Yeah.
It's fine. But no satisfactory answers have been provided.
Okay. There's a question at the back. Oh well, let's have this one first.
I was quite interested that you mentioned the importance of having high-resolution spectra when you go visit the atmospheres of these planets. What I don't understand is, if you, for example, you've got a high-resolution infrared spectrum and you're looking at a gas, the actual resonances, the stretching frequencies and bending frequencies of, for example, CO2 or H2O or methane are pressure dependent and they're temperature dependent. So what you'll see is just a broad spectrum. So it's like looking with a very fine tool at something that's intrinsically very broad. What's the point?
Well, so on the current, the example spectrum there was from the Trace Gas Orbiter, which is now in orbit around Mars. And it's going to get a big signal. It's going to look at the sun as the sun sets behind the planet. So it's a nice bright source, a nice long path length. But also it's looking at very tenuous regions of the atmosphere where you have very narrow spectral lines because the pressures are very low. And also, when the constituents themselves are in very low abundances, then you can get very narrow lines. Your point is well taken about majority abundances, so the carbon dioxides and so on. But for the weak lines and the trace species, the lines are very thin indeed. No, this is an absorption spectrum we're looking at. But
We have time just for one last question. So this.
Hi.
Hang on, we can't hear that. Is it switched?
Hello?
Yes.
Yeah, sorry. You spoke a bit about the development of the scientific instruments which are used in exploring space more broadly. I was wondering if you had any insight into the development of the actual means to travel out to those areas, and in particular whether you see any development of a similar scale in that sense, or is it more just the way we measure once we're out in that space?
So, I mean, I talked about the science and the instruments, but of course, we rely on the rockets to get us there. I'm not sure what insights you're looking for. So the workhorse is the chemical rockets, but you can get great efficiency gains by going to electrical propulsion, and people dream of nuclear propulsion, but that's a long way off, like commercial fusion power. So there's work ongoing.
I know there are some more questions, but I'm going to have to draw it to a close because we're due to finish at 6. So before we thank Colin, I just wanted to draw your attention to the next couple of events in this series. Next week, we're heading in the opposite direction. It's called Exploring Our Inner Space, and that's not about meditation. It's about the deep sea, and it's Professor Alex Rogers, who's one of the directors of the Oxford Martin Programme on Sustainable Oceans, who is frequently to be found a couple of kilometres down in a submarine. So it will be a very different world that he'll be telling us about. That's again at 5 o'clock in this room next Thursday. The following week, Professor Sir Chris Llewellyn-Smith, who's Director of Energy Research at the university, will be exploring can future energy needs be met sustainably. So that's just the next couple in the series. And I'd just like to close by thanking Colin very warmly for a fascinating talk.
I could have put the